Agriculture has always played a vital role in human society. It has had a significant impact on the development of human civilization over the centuries, having influenced and provided human civilizations with the basis of real development in economic terms. It has traditionally needed the presence of favorable environmental conditions. Today, due to a rapid rise in requirements over the past decades, agricultural produce demand has skyrocketed, while increasing urbanization has simultaneously led to a decrease in usable arable land for agricultural purposes. This is putting pressure on nations to find a solution to the dual challenge of rising demand with a reduction in available land for agricultural use. In such a scenario, there is a need to adopt sustainable and optimized methods to improve agricultural yields from available arable land, without harming the environment. An increase in soil nutrient removal, due to increased cultivation of land, has led to an overall depletion of soil fertility. This may lead to an increased risk of future food crises for the world's inhabitants. Modern, computer-based optimization and forecasting techniques can be used to help prevent such a scenario. Various computational techniques, traditional as well as AI-based, are being used to compute the fertility metrics of soil samples. The main issues with these methods are the lack of transparency and high capital expenditures. Through the AI-based model proposed in this paper, we aim to improve and address the shortcomings by providing the farmers with the ability to predict and interpret soil fertility using a lucid waterfall plot, without the need for complex traditional analysis techniques, while at the same time, providing the farmer with a clear visual understanding on the reasons behind the same. Soil fertility refers to the ability of soil in a particular area to provide favorable chemical, physical and biological characteristics that help plants in their growth. The presence of fertile soil could be beneficial to the environment, providing an opportunity to develop a carbon-neutral ecosystem. It is an important metric as soil fertility is directly related to a plant's nutrition, and a continuous nutrient supply during the crop growth phase can maximize crop productivity. Moving on to our work, we have implemented a model that predicts the soil fertility of a given farm using the Python programming language and the scikit-learn module. The dataset used for this model is the Lucas 2018 topsoil dataset, that has 18,984 sample points of soils taken all over Europe. It is the largest open-source database of its kind, spanning across the entire geographic region of the European Union and the United Kingdom. When it comes to our model, there are three particular layers to this model. Each layer has its own purpose in the framework. Layer 1 is the k-means clustering model, that clusters the input dataset into 5 different categories based on input metrics concentrations and classifies each sample into 3 categories depicting relative soil fertility. Layer 2 is the random forest classifier, which takes in input soil metrics and predicts an approximate label describing the relative soil fertility of the input sample. Layer 3 is the explainable AI layer, which gives a human interpretable understanding of the values predicted by the model. The given figure shows 3 different waterfall plots from the third layer, which describes the impact of the metrics on relative soil fertility categorization. It can be observed in each figure that the pH_H2O and pH_calcium chloride have a huge impact on the fertility of the soil. A low or high pH_H2O and pH_calcium chloride value can impact the relative soil fertility rating of a particular sample of soil. Other metrics like P, N, OC, K, calcium carbonate, and EC also have a significant impact on the relative soil fertility rating of any given soil sample. Based on calculations on the predicted values on the sample dataset, it is found that the proposed model achieves a high score of 96.97% in terms of accuracy percent and 0.90 in terms of the F1 score. The results are further demonstrated in the table shown above. Similar implementations of RF classifiers in other papers achieve an accuracy of 72% whilst predicting soil fertility, implying that the proposed model can outperform existing implementations whilst introducing a layer of transparency often missing from other models. Also, due to the vast pre-processing involved and the self-generation of labels, the proposed model may also have less bias in the data compared to other implementations that use human-defined boundaries as constraints for labels. A future application could potentially be used in the real world as a soil fertility improvement guide, which could improve yields of certain crops over time. This figure demonstrates such a use case in a real-world scenario.